Well, good morning, everybody, and thank you for joining us for another event. It's UK Nuclear Advanced Manufacturing Research Center Advanced Manufacturing Technologies with the G4SR2 SMR webinar series presented by the Canadian Nuclear Society and the Organization of Canadian Nuclear Industries. My name is Joseph Bastien. I'm a manager of special projects, including the Advanced Technologies and Process Council for the OCNI. I'm here today with my co-host, Wilson Lamb, CNS G4SR2 International Conference Chair and Senior Nuclear Technology Advisor of the Ontario Ministry of Energy, Northern Development and Mine, Ontario, Canada. I also want to welcome Benjamin Rubin, who will be monitoring our chat today from the Canadian Nuclear Society, and our two very special guest speakers, Charles Carpenter, Senior Technology Officer of Nuclear AMRC, and Matt Smart, Project Technical Lead in the Nuclear AMRC Machine Technologies Group. I'm now going to hand it over to Wilson, and following Wilson, we're going to give a little bit of technical instruction on how to access the chat feature, and then we'll hand it over to Charles and Matt. Wilson.
Joseph, and welcome fellow attendees from Canada and around the world. Hope you all stay safe and well. I'm Wilson Lamb, the Conference Chair of G4 and Small Reactor International Conference. G4SR is a division of the Canadian Nuclear Society, a learned nuclear science and technology society with mandate to provide a forum to encourage Canada-wide and international participation and sharing of information on the development in Gen 4 nuclear design and small modular reactors and related science and technology. It is my honor to co-host G4SR webinar with OCNI, who offer very generous goodwill for CNS in sharing their webinar platform. G4SR2 is supposed to be held in November, with the launch of SMR Action Plan to implement the roadmap recommendation. Due to COVID-19, G4SR2 in-person conference is now postponed to October 2021. In this place, we will have a two-day virtual summit on November 18-19 this year, positioning to launch the important SMR Action Plan, together with 7 plenary sessions supporting the SMR Action Principles. To build the momentum towards the virtual summit and the in-person conference in 2021, we have a series of webinars. This is our second G4SR webinar. Today, we have probably over 250 registrants, amazing record of attendance, which demonstrate the level of interest on SMR. And I'm privileged to host today's webinar on UK Nuclear Advanced Manufacturing Research Center, Advanced Manufacturing Technologies. Advanced manufacturing technology are key to turning Gen 4 reactor design into commercial reality, from innovative cutting and welding techniques for specialist alloy to new approaches to modular construction. Charles Carpenter, Senior Technology Officer at the Nuclear AMRC, will introduce some of the technology and application under development at the center and explain how manufacturing innovation is helping cut the cost of new low-carbon generation. Charles is responsible for developing the Nuclear AMRC Technical Strategic Plan, creating and maintaining technologies roadmap, and managing capability development projects and board director research. Charles represents the Nuclear AMRC on the high-value manufacturing catapult technology strategy board. He advises several catapult technology and strategy teams. He is a chartered engineer and member of the Institution of Mechanical Engineers, and previously worked in quality roles at Aeron Electronics and Frederickson. Our second distinguished guest is Matthew Smart, Project Technical Lead in Nuclear AMRC Machining Technology Groups. He takes an in-depth look at the single platform manufacturing techniques developed through Nuclear Innovation Program, part of the UK Nuclear Sector Deal. Matt is responsible for overseeing and executing project research in a range of technologies. At the Nuclear AMRC, he has worked on project and technology, including manufacturability review of both current and future reactor technology, welding optimization, advanced fixture, digital integration, laser tracking, finite element methods in simulation, thermography, 5-axis robot programming, 3D printing, cryogenic machining, cooling. Now, before I hand over to Charles, let me acknowledge the tremendous support from Joe Bryan of Nuclear AMRC, Joseph and David from OCNI, and Ben and Amir from CNS. We will have a Q&A session at the end. If you have any questions, please use the chat box to send your question. So Joseph, hand it back to you, please.
Thank you very much, Wilson. And just to give everybody a little bit of background about what we do at OCNI, one of my roles is running the Advanced Technologies and Process Council. I think I like to say I have one of the best jobs in our organization because I am a giant nerd and a huge fan of engineering. And so I get to work on all these amazing technologies, number one of which is advanced manufacturing, but all the way down to artificial intelligence, natural language processing, nanotechnology. And I get to work with some of the greatest engineers and scientists across the nuclear spectrum. So this is advanced manufacturing is a huge part of what we're going to be focusing on in 2020, 2021. We're going to be doing bi-monthly subject matter expert events, including a blockchain event in September 2020, talking about the applications of blockchain to quality assurance and materials tracking. And we are now going to be announcing an advanced materials session at the end of October, pulling from across the nuclear supply chain in Canada and the CNSC to talk about what needs to happen from a regulatory and quality assurance and process view to get advanced manufacturing cascaded and adopted across the nuclear supply chain. We're also going to be running an ATP TEDx-style event in April 2021. That's going to include a summary report that will highlight all of the advanced technologies that you see above. So we really look forward to having all of you participate in these events, and hopefully we can have Charles and Matt back when we do our advanced manufacturing session in October. Gentlemen, we would love to have you. And without any further ado, I'd like to hand you over to Charles Carpenter. Charles, we are opening your channel now.
All right, thank you for the intro, and good morning and afternoon, depending on where you are. My name is Charles Carpenter, and I'm the Senior Technology Officer at the Nuclear MRC. And when I try to explain what I do to my nephew Caleb in Nevada, it's basically I get to work across all the amazing technologies at the Nuclear MRC, but I also get to go work at our sister companies and see some of the things they're doing in automotive and aerospace and the process engineering. So I get to see a little bit of everything, which is kind of amazing to be in that space. Okay, next slide. So for today, we're basically going to go over some of the kind of key challenges we're seeing, what the manufacturing innovation that's occurring at the Nuclear MRC, and then I'm going to transition into more detail into one of our kind of platforms that Matt's been working on and give you some more detail in that area, what we're doing. And then some of the future work that'll be going on beyond that. So next slide. So we start looking at the challenge. We all know we have a challenge. It's all around decarbonization. And in the UK, we have something called net zero by 2050. It's going to be a really challenge for us to meet that. We know that we need decarbonize kind of power generation for that. And with that, this is one of the studies done by the Energy Systems Catapult. And it's recognizing that to do that, we'll need to see an increase in low carbon technology to do that. And you can see in this particular example, nuclear will play a big part of that. But for nuclear to play a part of that, we need to realize we need to reduce the cost and other aspects of nuclear to make sure that we are playing our correct part in that. So hopefully, if we do things go correctly, we'll see a large increase in the amount of nuclear in the power generation to kind of take care of that base load, along with the other kind of renewables and other sources of low carbon energy. Next slide, please. So in the UK, we've had two big things come up, which is the industrial strategy, and with that, the nuclear sector deal. And these were released several years ago, but the key highlights of these don't change. They're pretty much the same. We recognize that we do need to increase our R&D spend to around 2.4% of GDP by 2027. And that's really to increase innovation and research in the UK. But as part of that, we also recognize that the nuclear sector needs a deal. And there's certain things we need to do to make sure that we're part of that and make sure that we're part of this kind of decarbonization of the energy sector. And to do that, we need to reduce the cost of new build by 2030. We also need to decrease our decommissioning liability, the cost to taxpayers, by about 20%. And to do that, we also need to realize about the supply chain. We need a competitive supply chain that's engaged in participating in the nuclear sector. As you can realize right now with COVID-19, we've seen issues with supply chain and the resilience. So this is of interest right now, is how we make sure supply chains are still competitive. And as we kind of move out of this COVID-19, what does it look like for our supply chains and make sure they're resilient and ready to engage in the nuclear sector. There's also part of the sector deal, we're also looking at innovation, recognizing that we need to look at the next platforms for energy production. And part of that, we have fusion, because the UK has always played a big part in fusion. There's been a big investment in the National Fusion Technology Platform and also around advanced modular reactors. And for us in the UK, SMRs do fit in this kind of advanced modular reactor area, so that's part of where the funding comes from that, is part of that area. All right, next slide, please. So before I was talking about kind of supply chains changing, a big thing for us is industrial regeneration. And this is the site of the nuclear MRC right now in 1994. It was an area of a large kind of mining and coking area. In the 1980s, this was an area of the kind of mining strikes. It kind of shows how industry has changed. So if you move on to the next slide. So this is that same site today. And the idea is industry is changing, supply chains are changing. So as we look into this, what does that really mean for the manufacturing sector? So if you look at this sector, this cluster where the nuclear MRC exists, in the right bottom hand corner, that's McLaren's new composite facility. As you move up, UKAEA is introducing a fusion materials center. And also in the center of that is Rolls-Royce's advanced blade casting facility. And then on the left-hand side of that, you start seeing the research organizations. So the nuclear MRC, obviously focusing on the nuclear sector, and next to it is the AMRC, which focuses on the aerospace sector. And because of this cluster, we've also been able to bring in other industry partners into this region. So you can't see it on that picture, but on the outside of that picture, Boeing has their new facility on that site. So it's showing how we're starting to see pull-in industry into this area, this kind of cluster of innovation and industry partnering to progress the manufacturing sector. And on the top side of that picture is where we have our training centers. This is where our apprentices start learning new manufacturing kind of to work into the manufacturing sector. So they're working on machining apprentices, welding, and kind of automation apprentices. And hopefully one day we hope to get more engaged in the nuclear sector of these apprentices. At the very top of that picture is a community. So that's the new housing community that's going around this kind of industrial estate, showing that now that community is part of the kind of manufacturing landscape. So me, myself, I actually live on that estate with some of my colleagues. So when we do go back into work, hopefully it's a nice little 10-minute walk to work. So I do that every morning, a type of kind of walk to work and walk back home. So it's kind of a new changing form of manufacturing and how we work. All right, next slide, please. So next I'm going to go on kind of who we are, the nuclear MRC, so kind of focusing more on our manufacturing innovation. So if I can go to the next slide. So there's two key areas where we really kind of do this. And one is manufacturing innovation. This is really working on kind of reducing supply chain, reducing cycle time and increasing quality. And how do we reduce lead time and reduce cost and risk? So how do we kind of de-risk some of these new processes for the industry? And also developing new technologies and new techniques to improve the manufacturing industry. The second part of that is supply chain development. So we can't just develop technology, we also have to develop the supply chain so they can use this technology and kind of implement those benefits to the sector. So with this kind of supply chain development, we're trying to raise the quality standards of the supply chain so they can actually compete in the nuclear sector. So next slide, please. So on this slide, the biggest thing I want to highlight is if you look down on that shop floor, you can see it is an industrial shop floor. So we recognize that we need to be in an area that we can take innovations from universities and academia and scale it up for industry. To do that, we need to actually be the kind of equipment that industry is using. So you'll see that actually we have the same machining centers you would see in industry, the large laser and electron beam welding cells. So not just small little applications where it's solely for research, but how do you scale it up so it's actually industry ready. That's a key thing for us, making sure things are ready for industry to use, not just in the lab where we keep inventing it, or for kind of just research. So it actually goes from research to actually use. That's a big thing for us. So next slide, please. So to do this, we have nine anchor technologies. So I'm not going to really read through those, and then you can read through them yourselves, and I believe these slides will be shared, so you can go into more detail on these. But with these first three, the key thing I want to note is you'll notice they are across all sectors. All sectors are looking into additive, kind of simulation and analysis, and automation and digitization. So this is key things that we can work across other centers and look at what aerospace is doing, look at what automotive sector is doing, and look what process industry is doing, and recognize that we can pull quite a bit from them to what we're doing. So these are actually very cross-cutting technologies. And we're working quite a bit with other centers across the UK and internationally to advance these technologies and see how they fit into the nuclear sector. And in those two pictures there, you can see that we are doing quite a bit in the kind of virtual reality area. That's a virtual glove box. The top picture is our isostatic pressing unit, which is actually on the sales guide that is useful to industry. So next slide, please. So the next three anchor technologies on this slide I want to highlight is kind of controls and instrumentation. Mostly this is because this is a new area for us. We spent a lot of time in our kind of inception working on large metallic parts. And we realized that assist the nuclear industry, it's more than just that. We've talked about manufacturing. So we've recently developed a new center in Derby, in the Innovation Hub. This is where we're looking at our kind of controls instrumentation, a lot of work in sensors, a lot of work in kind of digital engineering kind of arena. This is becoming a bigger area for this. You'll see more from us in the future on this. The second one I want to highlight is codes and standards. So this is one within the technology team we debated for a while. And we recognize that you can't just develop the technology without developing the codes and standards with it. If you actually want industry to use it, you got to make sure you're developing everything from the regulation, the codes and standards to make sure it can be in use. So that's been a key area for us, and you'll see more from us in this area. We are starting to get more involved in things like the ASME Code Week and recognizing how do we start progressing some of these items so that advanced technologies can be used in the manufacturing sector for nuclear. In those pictures, again, just highlighting, we're looking at kind of industrial size applications for our technologies. That's our electron beam welding chamber on the right. That is, from our understanding, one of the largest in the UK. So it's a 208 cubic meter vacuum chamber. So we're looking at the size that we can actually fit large vessels in there. So I think that vessel on that table there is over 2 meters. So it's on the order of like 6 to 7 feet in diameter. So we're looking at things that are actual size for industry. Next slide, please. And these are the last three kind of anchor technologies that we're working on within our center. Again, highlighting the size-wise range within our technologies. So the machining technologies, you can see we are working on vertical turning lathes that are on the order of large vessels that you'd see for manufacturing of a reactor pressure vessel. And that's important to us to make sure our technologies are relevant. And you can see that in those pictures. And that bottom picture kind of highlights our process and verification validation. So this is one of our heat exchanger projects. You can see that we did quite a bit of work on the metrology aspects of it and how can we do a lot of the verification and increase that process. There's quite a few case studies on this on our website, which we can direct you to, showing that we were able to reduce significantly the amount of time required to inspect this type of heat exchanger. Right, next slide, please. So within those 9 kind of anchor technologies, if you cut across those, we're looking at what kind of critical programs can cut across all those. So we have 6 of those at the moment. And the first one is through life engineering services. And for us, we've recognized that the way industry is operating is changing. We aren't just supplying components anymore. There's a lot more services that go along with when you supply high value assets. So we're looking, and we're also gathering a lot more data. So as you gather more data, there's more things you can do with it. You can start looking into predictive maintenance and working more with your customers to provide services. And we're seeing this is a big area that's been developing lately. And one of the prime examples that gets kind of quoted quite a bit is Rolls-Royce's Power by the Hour. They're offering a service to the airlines. Now, it's debatable whether that's kind of a good service right now without airplanes flying in the aerospace insurers right now, but it is a new service model, and we're seeing quite a bit of interest in those type of models in the future for areas like this. The next item is the automated platform manufacturing. This is the one that Matt will give you more details on later, one of the key projects in that area. So we'll move on to that area a little bit next. Our next one is kind of safety design, system architecture, and equipment qualification. So we've recognized that all our technologies need to be able to link into this area, especially around design. And we start looking into, if we sort of get the supply chain ready for this, we need to get them understanding equipment qualification. So this is actually quite linked into our supply chain development also. It's kind of the system area. The next kind of key critical platform is around standardization. And the next one is modularization. So with modularization, we've started to develop a new center over in the kind of Birkenhead area. This is next to Liverpool. As we recognized, especially with small modular reactors, there's quite a bit of interest in this area in developing this. So we're working with the shipbuilders in that area to understand how can we bring their technology to our area, their philosophies on modularization, and bring that to the nuclear industry. So we're kind of right in the heart of that within the shipbuilding area, within the kind of Liverpool, Birkenhead area. The last one is reconfigurable tooling and smart facilities. So if you look at that image on the screen, that's the kind of our token image for reconfigurable factories. And this is our Inform project. As you notice, it is our symbol making up that kind of design. And to start looking at how we kind of track assets across the facility and how we start developing how we lay out a factory. So you can start looking at taking advantage of these new things that are coming out in terms of smart factories and digital kind of environments. So with that, I'll move on to the next slide. So going into more detail about this automated platform manufacturing. So for us, these critical programs are visionary programs. So it's more than just one single project, and they're over many years, and it takes many partners to develop something like that. And so we ourselves can't deliver that platform. It's going to take a lot of work with our partners to do that. So see, these are some of the big projects we've had over the last several years that are looking at us as we start to move towards that kind of platform. So one of the first ones we have is something called Baseline. This is working with a company called InSphere to look at how do we start looking at on-machine inspection. So looking at some of their technologies and how we start integrating with that with our equipment so that you can actually start moving towards on-machine inspection. The next one's called AMOS, and this is really looking at additive repair for aerospace. And this is a project we had with quite a few Canadian partners, looking at how do we look at our systems that we can start scanning a part and having that system recognize what it needs to do to repair that part, come back and scan it to verify that the actual repair was done correctly. It's kind of moving that those kind of systems on. So one of the ones that Matt will be talking about more today is our single manufacturing platform environment. This is really looking at how do we start automating kind of welding processes. As we start automating those, how can we start integrating those more into the kind of equipment that we have on our site. As you can see, that's one of our big machining centers. So we can start automating these processes, making them more autonomous. How can we start linking that more into having multiple processes on a single platform? And the last project I want to kind of link in this area is Caroma. And this was we call a Horizon 2020 program with several European project partners. And this is really looking at kind of autonomous robotics on a manufacturing platform. You can see those robots are working with the machining platform. So as that machining platform is working, one of the robots is working with the machining center to apply pressure to the back of the part to reduce vibration. We have other robots working on deburring and kind of polishing of welded areas. So you actually have a center that's actually doing multiple things instead of just one application. So obviously in the machining center, you can't have people on that site inside the manufacturing platform while it's doing it. If we introduce robotics to that system, what else can we do in that system while it's actually machining that part? So if we look at this as a big vision, and obviously it's good to have these kind of big visions to work towards. We're looking at how do we enhance the autonomy of manufacturing? How can we look at kind of process cognition? How can we get our systems to scan the part and recognize what they need to do? How can we start integrating these processes into a single platform? And with all our projects, we're looking at how we're collecting lots of data. So everything, that's one of the big new things. There's lots of sensors. As we move in our modern day lives, data is being collected everywhere. We're also seeing that in the manufacturing environment. So as we collect all this data, what are we going to do with it? So we're looking at kind of predictive and prescriptive analytics. And then one of my coworkers over in the AMRC, working in the aerospace divisions, which he has this kind of saying that I always like to bring up is, it's just data until you can bring it to the right person, the right format, the right time. And once you do that, your data becomes valuable. So how do we start linking in? How do we do that? So with that, that's the end of my presentation. So I'll be turning over to Matt Smart right now to kind of bring in more details on the Simple and some of our future work in that area. I'll turn it over to Matt.
Hi, Charles. Thank you for the introduction. And thank you and welcome to you all this sunny afternoon in Sheffield, or good morning to those across the ocean. So, yes, as Charles said, I'm going to be touching on one of our key projects within the automated manufacturing platform strands within the Nuclear NRC. So if you move on to the next slide, please. So yes, so the wonderful acronym of SIMPLE, where the project is anything but, is Single Manufacturing Platform Environment. So the concept is one of the core technologies that goes across the centuries in terms of reducing lost value time due to rework, component moves, and so it's increasing productivity by co-locating processes on a single machine. So that could be closing the loop between welding and post-welding inspection, between machining and metrology, potentially between weld preparation and welding. It's the idea between bringing as many processes into one component, one location on one component at a time, but to address the significant challenge that you face when in the nuclear industry, when you go up to the components that you face in terms of the size, the complexity, and the difficulty in moving the components and setting them up on each of the discrete machines. So, so the concepts that were drawings that came out of the initial scoping work were something akin to our Salute machining center, where you have you already have a capability to interchange heads for different machining operations. You then develop specialized heads for machining inspection, 3D metrology, light welding work, or NDT inspection. With the idea that you already have the components set up, you already have your reference frames and datums established. If you need to do any processes, you can do them on the machine there and then, and for any rework, and then you're back onto the main operations. The potential downside you have to this technology is obviously you're creating one potential bottleneck. If you're having all of your processes on one component, and it's going to be sitting up there on that one machine for months, then it becomes you have to balance that against what the throughput of your factory is. So for large single high-value items that you encounter in the nuclear industry, it becomes more viable for this concept. So next slide, please. So as Charles touched on, these programs are long multi-year development programs. So while the first phase is simple, while the acronym is about the single manufacturing platform, we focused entirely on one of those concept heads in essence, in terms of focusing entirely on one manufacturing process to bring it in line with the quality standards and inspection methods that you encounter in the others. So we focused entirely on arc welding with the view of integrating process monitoring sensors and alongside non-destructive testing to bridge that gap between welding and inspection. When you're performing fixed section welding for pressure vessels, because there's so much uncertainty around the defect rates of the process and the high cost of finding flaws late in the process, it's very common to do what's called interstage NDT. So you're not performing a final inspection, but you're performing an inspection partway through the weld through your process. So that would be, say you deposit 10 to 20% of your fill volume. You then pause the process, cool it down, move it to an inspection area, take your volumetric inspection, pass it through. Then if there aren't any flaws, then you can bring it back to your process, bring it back up to temperature, and then carry on. Or if you do find flaws, then it has to be sent to a rework area. But this workflow is established so that you don't get to your final inspection, then find that you've deposited a flaw at the root of the weld, then have to grind through 100 mil of previously deposited weld, and then go through a very arduous repair strategy. So the idea between this technology is that we establish a baseline suite of process monitoring sensors to monitor the arc as it's and weld as it's being deposited. Then we also have an in-process volumetric inspection technology to give an in-process check. Because of the difficulties and challenges of doing this while the material is hot and in the welding environment, you won't get a full qualified inspection, but it'll give you an indication towards whether there are anything worth flagging or whether you need to halt the process. So the whole system is, in essence, is giving you more process security so that you don't have to pause the process unnecessarily to do an interstage NDT. And that's how we drive up productivity, and that's how we bring down costs of these components. So, like I say, so phase one was very much focused on the automated weld monitoring system. And then with how the funding stream was set up and how we plan on moving forward, we then plan on bringing that technology into the single manufacturing platform environment and bringing in more technologies within one manufacturing cell, whether that's within a machining center like the Soluthe, or whether that's just many robots co-located around a large component, as in the Corona project. So next slide, please. So within simple phase one, so this is simple in essence of the entire project as it stands. So this was started back in early 2017 and concluded in the summer of last year within this phase of funded work. It covered a broad range of sensor and other technologies centered around arc welding of various states of maturity to give us a full spectrum of what's going to be around the horizon and what's readily deployable on arc welding challenges, the components and challenges that we're facing now within the industry. And because of our funding source, with it coming from Bayes, they're very keen on us developing technologies close to deployment so we can start realizing benefits to the economy as soon as possible and and to maximize the amount of market opportunities that these technologies could exploit. So across the consortium, so this consisted of the University of Sheffield, so that includes the Nuclear MRC, the AMRC, and the University of Sheffield Physics Department, each having their own strands of work. And then in addition, we partnered with the University of Strathclyde, Centre of Ultrasonic Engineering. One of their partners, Peak NDT, is a small SME NDE equipment manufacturer. And then we also partnered with the Welding Institutes to bring in their expertise of vision monitoring. So like I say, the discrete work packages were novel weld modeling techniques. So these aren't traditional FEA and finite volume methods. So this is using machine learning and neural networks to try and do geometric modeling. TWI leading work on machine learning on vision systems. As I said, the University of Strathclyde and their equivalent catapult center, the AFRC, looking at in-process ultrasonic probes. Work delivered by the Nuclear MRC on acoustic monitoring, laser profile capture, an emerging sensor technology down selected as ESPI, which I'll go into detail in a second, and then ultra-high frequency in-process signal monitoring, led by the physics department at the University of Sheffield. And then it was the AMRC design and prototyping group who built the data monitoring system for us, and then integrated our sensors into the demonstrator technology. So touching on the demonstrator, so this was selected as a demonstration of large pressure vessel welding with gas tungsten arcs welding, and with a proof of concept of concurrent data collection of all of the sensors, and then early proof of concepts for the analysis methods for the detection of conditions that could lead to welding flaws. So next slide, please. So I'll start with the lower TRL development. So this was kind of viewed as a pipeline for future research and establishing if there are any game-changing technologies around the corner. So ESPI, or electronic speckle pattern interferometry, which rolls off the tongue. This is a method it's a non-contact method of measuring strain. And when you induce a deflection, you can actually measure residual stress. And this has been proven in concepts at the university scale on small established samples that have been well studied. So we took this core concept and we were looking at scaling it up to something that can be effective at scale on components that are relevant to the nuclear industry. So because there wasn't really anything on the market that was capable of testing the methodologies that we wanted to do, this work package was about developing a prototype transportable ESPI units that can do both in-plane and out-of-plane electronics shearography, essentially, to evaluate whether it would be capable to measure this strain. Whether that could be then correlated to residual stress on a large component in process is multiple years of further development, but we were just establishing whether the sensors are going to be capable of at least capturing that information. And even if you couldn't tie it to residual stress, measuring macroscopic strain in terms of deflection would be useful as an established in-process methodology. So while we only established fundamental testing with this, it was promising, but the challenges of actually performing this into a welding environment meant that we're carrying on with the technology, but in other applications. The next slide, please. So the other low TRL application that we developed, evaluated through the course of the project, was use of neural networks for modeling of welding processes. So the concept behind this work was establishing your input parameters into the welding process. So essentially your welding procedure, your specification of material, your filler, your welding parameters, conditions leading into the process, and then you can correlating that to key parameters around the weld that's output. So for each pass, finding out the weld thickness, the size of the heat affected zone, the penetration, the toe angle between the deposited weld and the wall and the subsequent layers. And then as you can build up that model and increase its accuracy for your selected process, you can then start looking at back propagation of that neural network. So once you've got this established, the ultimate aim of this technology is to then select your desirable parameters, so toe angles that promote adhesion into the sidewall and to alleviate lack of sidewall fusion, or conditions to alleviate against wormholes. You select your conditions, the desirable conditions that you want, and then the program will back propagate and give you a suite of welding parameters to test that will give you more favorable welding conditions. So the idea is this is a useful tool set for establishing new parameters and for welding new components. So this could be highly translatable to SMR or AMR technologies. However, this is very early days in the technology in terms of the amount of data you need to collect to train the network, how selective it is against each of the materials and specific joint designs. So there is promise there, but again, this is lower TRL work that we were just investigating in terms of this could be incredibly useful, but will we be able to develop such a toolkit for it to be realized within the timescales we need for creating first-of-a-kind plants for the next generation nuclear. Next slide. So it was initially lower TRL technology at the beginning of this program, but the rate of development has been very impressive. And this is providing us in-process volumetric inspection of not necessarily the weld, but a recently deposited weld. So the challenges for in-process UT is quite considerable in terms of the traditional piezoelectric transducers stop becoming piezoelectric above a certain temperature threshold, and your welding and preheat temperatures are significantly higher, so you have to have cooling and heat management considerations. The ultrasonic couplant that you use to interface between the material and the probe to transfer the ultrasonic impulse. The majority of those will either boil away at the preheat temperatures you're using or have the potential to contaminate and run into the weld and cause their own defects. You then have EM interference from the welding process and the arc itself, and the high power sources that you incur in thick section welding. You also have temperature issues due to if you've got strong temperature gradients throughout your workpiece. The speed of sound in that material will change, which presents a challenge to sizing the defects accurately. And then additionally, you also have a system that's designed to detect and quantify interfaces in material. And prior to welding, you have a full interface. And then as you're depositing each layer, that interface changes. So it's how you mask and prevent the system from detecting just the edge of the weld and the weld preparation as you're filling through it. So there are a lot of challenges that need to be overcome. And by the end of the simple program, we were able to demonstrate collection data at 150 degrees C, modeling techniques to compensate for the temperature profile, automated collection of the probe of the data on the probes subsequently after welding, and integration of the entire system within a robotic welding cell. So this was performed by our partners at the University of Strathclyde in their welding centre. So a significant stream of the future work of this program is working with them continuingly to develop this technology. Next slide. So I'm now going to touch on the work that was completed at the Nuclear RC as part of the demonstrator for the project. So, so the equipment was a Polysude NG8-300. So this is a narrow groove welding head that's capable of working on components up to 300 millimeters deep. We wouldn't typically expect those kind of thicknesses in the applications we consider, but common, or on the upper end, we could be at 150 to 200 mil. As Charles was saying, the equipment is representative of the scales that we encounter in industry. So it's a common boom with 6 meters horizontal and 4 meters vertical travel, implementing cold white TIG. because we were funded through the Nuclear Innovation Program and to demonstrate the largest potential cost reductions, we focused on pressure vessel steel welding. So we selected a SA508 pressure vessel steel according to specified as the Joint Standards, the Common Welding Standards. Just as a caveat, I'm not a welding engineer, so I will probably butcher all the terms, just like me working this project for so long. But that's my get out. But so obviously to actually do a fully representative weld would be inordinately expensive at this stage of the program. So for the proof of concept, we were using representative materials at representative thicknesses, but we were just using flat plate welding coupons just to simulate a large vessel with minimal radius, just for ease of the development and help it improving the application of our trials. So yes, so the next slide. So within the system, we were demonstrating three sensors into the data acquisition system. So that's 3 on the head in conjunction with the power monitoring. So as I said, we've got 2D laser profile set up, scanning ahead of the weld to inspect the weld geometry. And then as we're doing multi-layer welding, we're inspecting each of the subsequent layers as they're deposited. We've got acoustic monitoring, listening to the arc and looking for disturbances into the acoustic profile given off by the welding. A weld vision system retrofitted to the weld head, implemented by TWI. All of this is feeding into a data acquisition unit that was massively overspec'd for our immediate needs, but because we knew this was going to be a future development platform, we developed an open architected and significant computing power to enable us to implement some of the machine learning and AI algorithms in future programs, and then also bringing in the power monitoring system developed by the University of Sheffield Physics Department. So next slide. So there was a lot of development and work done within these work packages, so I'm only going to touch on a few of the footnotes. So the concept between the process monitoring for the power is that there is already a power monitoring system within the control system for the welding power source, and this is to control the distance between the weld tip and the weld pool. So it's called a arc voltage control. So this maintains a constant voltage by adjusting the distance between the arc. But the system developed by the physics department was working on an order of magnitude of about 100 times faster than this current system. So this is looking for high frequency fluctuations and disturbances into the welding process and correlating that to welding flaws to enable us to flag conditions as they occur in process. So they previously had a proof of concept system that had been established onto tube sheet welding, rated to 50 amps. So their work was a lot of hardware development and scaling this up to be rated for the industrial scale, so going up to a 500 amp system initially and ready to go up to 1000 amp, and then establishing the methods in which they can train their system and do the signal processing to find these flaws as we start moving towards industrial applications where we start simulating the conditions and flaws as they're deposited. Next slide. So the acoustic monitoring. So there's been a lot of previous research into this field, especially in the academic community. I think there's quite a natural view on the ability of a welding operator and a welding engineer to listen to a weld and determine whether things are going correctly, right or wrongly. There's been a significant amount of research into the university side of things in terms of correlating the acoustic profile to things like weld penetration, size of the heat vector zone, etc. So we were looking at taking those core published methodologies and then implementing them onto our system and then evaluating which of them would be the most effective for our application. But one thing that we encountered and then had to engineer around was the fact that we're an industrial environment. So it's not as if you can ask the operators to stop talking in the next cell. We've got cranes moving overhead. We've got other processes occurring nearby. So you get a lot of it like process noise and disturbances to the signal. So we actually were implementing active noise cancellation with the second microphone to enable us to improve the signal to noise ratio and just to help mitigate against any of those unforeseen events. Then we were moving into analysis methods of the signal, and this was quite early work, but we did display quite a good correlation between our baseline welding conditions and then a suite of different parameters that can lead to common flaws like lack of sidewall fusion. So in the test suite, I don't know if you can make out the graph, but we were looking at sidewall arcing, travel speeds too high, interruptions to gas, those kind of potential situations that might lead to a flaw, and we can hear them and clarify them within this sensor. So next slide, please. Moving on to the geometric verification. So this is the laser profile scanners. So this is quite an established technology within other fields of welding in terms of using a 2D line profile scanner ahead of the weld to verify either that the weld torch is where it needs to be in respect to the weld preparation, monitoring things like distortion and gap of the components, and implementing that kind of closed loop control, traditionally on robotic welding applications in other fields. However, as you move towards the fixed section welding with narrow groove geometries, you start encountering a lot of challenges for the laser scanners in terms of reflexivity, line of sight. If you're trying to look down a cavity that's 100 mil deep and it's only 20, 25 mil at the top, actually observing that profile can be very challenging. So we were investigating different methodologies in terms of using single scanners, dual scanners, and then combining the signal in real time to then give us a full picture of the weld. And then using that information to feed back into a weld monitoring system in terms of, so you can monitor offset between the two parts of the workpiece, distortion, gap width, the position of your weld torch relative to the sidewall, giving you a log of relative position of the welding torch within the weld as you're depositing through the fill. So next slide, please. And finally, moving on to the vision monitoring system. So there are already cameras integrated onto a lot of these welding torches, and including the one that we have with the polysuit. So the quality of the image tends not to be too great, partly because of the challenges of they're actually embedding their camera within the weld head. So getting that signal out of that harsh environment can be quite challenging. And the method in which that's output and can be interfaced into other digital systems can be quite tricky. So we were using a top-of-the-line HDR weld vision system, and then tying that into a neural network to classify each of the welding frames against conditions that can lead to flaws. So this is prior work performed by TWI that they transferred into this program, and developing this technology to deployment and scaling up. So while they were able to give quite good correlations between the welding frames, one of the issues that is commonly encountered with the amount of data that you need, the data you need for machine learning, and the amount of time it takes a skilled engineer to then input and train that algorithm for a very specific use case. So one of the main things that the outputs of this technology is each of these discrete sensors have been developed in very individual ways, and so they don't necessarily speak to each other particularly well, and the amount of skill, squarepness you need to get useful outputs for a very specific application could be very challenging. So we kind of became quickly aware that to move this forward and to actually have a deployable technology that can yield real benefit is that you need to make it as process agnostic as possible and to be able to self-train as much as possible. So that's kind of how we're led as the output of this program. Sorry, next slide. So yes, so as I said, this program concluded in the summer autumn of last year. We've since taken this core technology and moved it forward into another program. So this has been a partnership program with Cavendish Nuclear, part of the Babcock Group, Doosan Babcock, and the University of Strathclyde, with ourselves. Again, with the fantastic acronym, so this project's called AWESIM, which is Advanced Welding Equipment System Inspection and Monitoring. So this project is combining, or further combining, the in-process ultrasonic transducer developed by University of Strathclyde, developing that into a roller probe sensor technology, and then taking the process monitoring sensors and building that into a synchronized data capture system that can then analyze those, the output of those sensors live, and then give an indication of whether we need to interrupt the process. So to deliver that to a TRL7, we expect that to be a 3 to 4 year program to actually be deployed in production within their businesses. AWESIM is going to be funded for the first 12 months to demonstrate the in-process ultrasonic data collection on the simple demonstrator at the Nuclear MLC in the Q2 next year. So we fully expect to be presenting this work at the G4SR online conference. So hopefully, if this has given you enough information, you'll be keen to hear about it in the next presentation. So next slide. So that's all for me. So I'll hand back over.
Perfect. Thank you, gentlemen. We're going to open up for questions with Wilson Lim now. Wilson, I'm opening your channel.
Yes. Thank you very much, Charles and Matt, for your very insightful presentation of your research project at the Nuclear AMLC. It's amazing about this advanced technology, advanced manufacturer can do for the next generation of SMR and advanced reactor technology. Now, I can see also you mentioned the neural network, artificial intelligence. Maybe I start off with a question, then I go to some questions from the attendees who give us the advanced question before the webinar starts. Do you see a convergence of advanced technology in the next generation SMR working with advanced material, computational, manufacturing sciences, as well as 3D printing, AI, and big data to advance the reactor core design? Maybe I start with you, Charles, first, and then Matt can add, please.
So that works. So for IC, there will be a convergence. Obviously, these are all key areas that are important to the nuclear sector. Obviously, we need new materials. Any kind of modeling and simulation require computational developments, anything in manufacturing sciences. And obviously, 3D printing will be a key area that kind of moves on forward. But we're also seeing key things like, for us, like we see the NRC starting to hold workshops on advanced manufacturing technologies. So we're starting to see the regulators interested in the convergence of these technologies, and that's good because that does show there's interest. And if we move these forward, we need those kind of groups looking at what we're doing and saying, yes, what you're doing, we will be on board with that, and we can progress that forward, especially in the area of safety cases and kind of code cases as we move forward. But one of the key things I want to highlight is obviously, in reality, we need the business environment pushing this forward also. So things like Matt's been doing with Simple and Awesome, it's got to bring together some of these aspects because we do have a funding partner, and it does bring technologies that can be used across multiple sectors. So obviously everything they're doing in Awesome and Simple can be deployed in nuclear, but it can also be deployed in oil and gas and aerospace. So we've got that cross-cutting technology that brings that interest to it. So for us to kind of get continued kind of convergence in the nuclear sector, we really need to start seeing kind of new builds going on to drive that interest and keep driving this convergence in these kind of advanced technologies. So with that, I'll turn over to Matt.
So yeah, so in terms of my view, just in terms of being on the ground floor of delivering R&D within this sector, I think it's some the benefits that we see is not in so much the direct cost reduction of the components going into the plants, but the reduction in costs in the development of those components in terms of rapid prototyping, creating fixturing for one-of-a-kind components, those kind of high incurred costs of developing a first-of-a-kind component and reactor. I think that's where cost reductions can really be made through things like 3D printing and advanced modeling techniques.
Okay, maybe just a follow-up, if I may. Because to have a convergence investment, you might have integrated domain expert working in different area and try to interact with one another to solve a problem. So in your nuclear AMLC, I believe you have maybe cite your experience where you integrate the domain expert from different area and try to interact as example how this can nurture the development of this convergence.
All right, I guess I can start with that one again. So the question I got is how do we get our domain experts kind of working across kind of technologies to kind of converge onto to accelerate this convergence? And I kind of highlighted that earlier with our kind of 9 technology anchor technologies. We have our key leads in those areas, progressing those areas. But for us, we also have these kind of cross-cutting, like I said, those kind of programs, critical programs. That's where we're really trying to drive that convergence. So areas like through life engineering. So we kind of can bring our digital experts along with our kind of welding experts and joining experts together to advance something. That's where we're really doing that is on those critical programs. So we do need those kind of programs to bring people together for a common issue to kind of accelerate and drive that convergence.
Great answer. Thank you.
Turn over to Matt.
Yeah. I guess the other thing that I'd touch on is in terms of how our center is structured with because we're part of the high value manufacturing catapults, we're constantly engaging with other subject matter experts from other industries, and because this flows through to us and the 7 centers across the country, that engagement really drives that cross collaboration and being aware of what else is realizing cost reductions in other industries and where we can pull and lead on expertise from each other.
Yeah, excellent answer. So, okay, maybe I move on to the next question. As you know, SMR being small footprint, integrated components, sometimes sealed vessel. Now, for inspection, this is quite difficult because it really cannot open up things. Now, maybe I can inject a question, which is, kind of like hypothetical. Maybe it's real. Can 3D printing allow us to embed and incorporate components into other material structure, for instance, sensor for components health monitoring? If this can be done, it would be very useful to reduce system monitoring costs. This process would create a very reliable self-monitoring diagnostic system, particularly for a sealed system. Any piece, kind of explore this subject?
Yeah, thank you for the question, Wilson. So 3D printing offers a lot of avenues for incorporating sensors into components. Obviously, there's a lot of ways to incorporate sensors, and we are seeing a lot of interest in how do we start collecting data, and then how do you start using data. So we're seeing a lot of the thing moving from how do we move from like just experience to data-driven decisions. So how do we collect that data and then make decisions with it? So there's from what I can see, obviously we've been told about this digital twin for a long time, this kind of hyped item of what it's going to provide us. We're actually starting to see some of these kind of things flow through, things about how can we start collecting data and actually using it. So I think there's kind of going to be impact in that area, especially in cost reductions on the in operations. But kind of moving beyond that, there's also when we start using that data, so we start thinking what kind of new business models does this allow us to open up to? And I implied to it earlier with kind of Rolls-Royce, and they're kind of powered by the hour. So what can we do now that we're collecting all this extra data on these components? And what can we do with that? So certain things like currently we design our safety cases based on particularly the worst scenario we can see that component might see. If we actually know what that component's seeing and can predict it, do we actually improve the way we design our components and also improve the way we kind of do our planned maintenance? So not just kind of doing our maintenance on planned schedules, but how do we do our maintenance knowing when it needs maintenance? So I do see a lot of areas in this for progress and some areas for disruption and kind of paradigm shifts in how we kind of deal with our maintenance and operations. And this is also a key reason why we have the new facility in Derby, that innovation hub. So that's why they're looking in the areas kind of sensor development, data analysis, again, going back to how do we make sure that people are getting the right data at the right time in the right format. And also a big area around cybersecurity. We are collecting all this data. We need to make sure it's secure and how we do that. Those are big areas important for us and why we're developing in Darby. So let's turn it over to Matt.
Well, it's just one thing I'll touch on. That's like more from the view and how I've been looking in terms of aspect of simple is, so we are gathering so much data about the component as it's being manufactured, and we're getting a much better digital representation of that component once it goes into service. So having that massive information, and I guess it's through the benefits of digital twin and how things are moving forward, it's how you tie that digital strand between the initial state and manufacturing data and pushing that forward. So I think there could be a lot of benefits between embedding sensors within components for that view, but it's I think it's also just like it's that through life data that you need to start gathering. And another one of the benefits of developing this hot ultrasonic probe is for your in-process inspections or through life inspections, you don't need to cool your components down to do so. So it's like that's delivering additional productivity so it's like how we can use established sensors in new ways to also drive benefits.
Excellent. Thank you very much for the excellent answer. So now I go to the question sent by the attendees in advance. One of the questions is by Eric Saucy, Canadian Nuclear Lab. And the question is, what are some of the challenges in the qualification and approval of advanced manufacturing parts for nuclear industry?
So I guess I'll start again on this. So I started off my career in the forging industry, and within the forging industry, we have well-established kind of qualification procedures. We know what we need to monitor, our key parameters, kind of critical processes like heat treatment. So we know this kind of thing 4 years. We know how to do it, and we've built this kind of decades of information. So as we look at kind of our new manufacturing processes, we're going to face some challenges as we're not going to want to go through that same process. So I just take additive manufacturing, for example. We don't want to do that same process we did with the forging and casting and take decades to realize the kind of qualification of the process for these components. So we need to start looking at some of these other things we can start doing and how we can improve these processes. So it's looking at how can we start using things like the data that we're collecting on actually parts in service to start looking at the kind of modeling and simulation, thinking about how we can start using that to help assist us in our qualification of components, and also looking at how we actually kind of manufacture our components, because Matt was saying earlier about this, if we're constantly monitoring the component, making sure there are no defects into it, how does that change how we kind of improve the part? Can we verify and validate the part at the end? So these are also becoming very important, particularly additive manufacturing, where it's going to be very hard to kind of scan and validate and do all things like ultrasonic inspection of these parts once they're complete. So how do we start looking at when we're collecting this manufacturing data, how can we start using that as part of the qualification process? So I think that's going to be one of the key things we start looking at. It's kind of in situ monitoring of our manufacturing processes. So can I turn this over to Matt?
And I guess the other aspects of, in terms of the qualification from an automated platform manufacturer point of view, is that in developing this process inspection technology, we're aware that we're not going to make any influence into the regulator and the current codes. So even though we're gathering all this in-process monitoring data, there will still be you'll have to do a full inspection when the component is cold. But the ideal point is eventually that you can use the in-process data, and that's the fingerprint and the security that you have around that process as the qualification for that component. But the path from where we are now to there is going to be quite a long and arduous one. So part of this program is to actually engage with the regulator and bring them on board and establish, well, what is the route for you to be convinced and to apply that methodology of qualifying the process rather than the components, and then that's how you can innovate more quickly and to deliver better cost reductions on a timescale that lets us deliver them.
Thank you. And the next question from Tim Anderson from Akron Nuclear Services. The question is, what considerations are given to the pre-inaugural periodic non-destructive testing inspection required by both codes and governing bodies who regulate the nuclear energy sector? This is in regard to the new materials wetting process that may be used.
Yeah, thanks, Wilson. That's a Again, this highlights back to one of our 9 anchor technologies as codes and standards. So we just can't work on, say, a welding process. We understand what are the kind of manufacturing codes that go along with that. And with those, there'll always be some sort of inspection requirement. So we do need to integrate those two and look at those two. You can't just develop them in silos and separately. They got to be developed together, and you realize how they link together. So we are looking at that. And that's why, like I said, that's one of our key anchor technologies, and that's why it's going to be a part of all our kind of cross-cutting critical programs. So it is something we are looking at. So in terms of new materials, we are looking into that with our various kind of other partners and groups. So we recognize that as we look into the new kind of advanced reactors, we are going to need to look into new materials and understand the manufacturing processes that go along with those, and also developing the inspection methods along with those. So ourselves, we don't do much on the what I'd call the operational inspection, but we recognize that the items that we do for manufacturing inspection are very linked to what you do on site on the operation inspection. So we are starting to kind of move into that area a little bit more. But that, to this point in time, it's still kind of very in the kind of the infancy of for us right now. We will be moving into that space in the future. So with that, I'll turn over to Matt.
I don't really have too much to add, but it's just in terms of, yes, it's bringing these technologies and seeing where the opportunity for exploitation is. So as I touched on, hot NDT for through-life inspections could be quite a significant benefit. And that's where we are partnering with other centres that do focus more on the in-process. So that's where Strathclyde do quite a lot of their research is in for ultrasonic inspection for through-life. So we're kind of sharing and bringing that expertise across the nuclear research hubs in the UK.
Okay, great, thank you. So this is the third question from Sunny Shiu. And the question is, why has Nuclear AMRC chose to develop the new manufacturing technique involving a single platform rather than adopting a well-established manufacturing technique like in the automobile industry or aerospace industry?
I'm happy to take this one, Charles.
Yeah, sure.
Thanks for that.
I think this is focus on my project. You're right. It is quite a contrast to established cost reduction methodologies that have been developed and deployed across other sectors. And well, I guess the first point is the fact that we did consider that, and that was Charles touched on another one of our cornerstone projects from that the Nuclear Innovation Program, which is called Inform, where that is the principle, where you have an intelligent fixture and attached to the components, and as that component travels through the facility, the processes are brought to the parts. Whereas simple is kind of the antithesis to that, where you've got your components and stays in one location, and all the processes are co-located there. Because no one solution will address every challenge and every specific application for each component. Because challenges that are faced in large component manufacture, especially for nuclear industry, is very different to that faced in the automobile industry. We're not, even with SMR, we're talking about creating a dozen a year, not 12,000 a year. So because of the order of magnitudes are so much smaller, and the components are heavier and larger, and the manufacturing equipment is so much more expensive, that's where you start needing different solutions to the same problems that they encounter. So that's what led us to the single manufacturing platform route. It's where that lost value added time is in between and it's inspections, rework, and it's basically any time you're not performing manufacturing operation. And because of there's so much time in terms of moving components throughout facilities, from specialist cell to specialist cell, establishing datums, getting them set up on each components, and then moving into and then having so much of your production facility dedicated to rework because your quality standards are so high, it means that if you can keep the component in one place and work on it there, that's where you can realize a lot of benefit.
Thank you. We have a very attentive audience, and we just, from the live audience, we have only one question from Paul Chan. I think it's related to wonder if Nuclear AMRC work with other institute, such as Belgian Welding Institute, because they have a line investigating new welding methods. So I think the question in general, would you reach out in collaborating with other countries or who also involved in advanced manufacturing or new welding techniques for a new generation of advanced technology?
So Paul, it's good to hear from you again. It's been a while since I've heard from you, but to answer your question, we do look outside the UK for international partners, and we are aware of the kind of advances in the Belgian Welding Institute and the technologies they're working on. At this time, we're still evaluating that technology and seeing how we could implement it within our facility and within our research strands. So we're interested in that. If we look at the bigger, wider international kind of research community, we are quite engaged. Like I said, we're quite engaged across Europe. We're also quite engaged across North America. So we're looking for these opportunities and where we can engage. So, for example, one of our largest projects right now is a 2/3 SMR program with EPRI, looking with the DOE, looking at how we can advance this kind of SMR development and reduce the manufacturing time of SMRs. And also working quite a bit across the EU. Like you saw the Chroma project, with all those European project partners on that. So we are quite engaged across the research community, across internationally.
Yeah, thank you. I would also say that in Canada, we begin to look for, kind of collaboration. I mean, talk about on behalf of Canadian Nuclear Society as a technical person here. I mean, Canada, as we know, we're going to be launching the SMR action as we have the SMR roadmap in 2018. So I think one of our venture is to investigate more and collaborate more with other countries in advanced manufacturing, because I think this is a paradigm change in the SMR deployment and manufacturing, and we cut costs and improve reliability and safety.
Yeah, absolutely. We absolutely agree with that.
Yeah. Okay. Because of time, I know that there's also advanced questions submitted. What we have, because we are limited by time, so there's some question that the nuclear AMRC would like to, talk to an expert for full response. What we do, we intend to provide a written answer to those questions, and we post it in the CNS email announcement or website, so that those people who attend this webinar able to see the response to their questions. So I think anything to add from Charles and Matt before we close this webinar?
Just to thank OCNI and CNS for hosting this and allowing us to present on some of our projects. Well, thank you.
Yeah, we are also very grateful for the two distinguished speakers to speak on this very illuminating advanced manufacturing projects in your nuclear AMRC. So thank you, and I'd like to end just to announce that our next webinar will be on August 20th. It will be conducted by our distinguished guest, Dr. Livy from CNSC, to talk about integrated safety assessment methodology. So please stay tuned from our CNS email and our website announcement. So I give it back to you, Joseph.
Perfect. Thank you very much, Wilson. Well, I just want to say thank you to Wilson and Ben from CNS and Matt and Charles from NAMRC for joining us today. It was a really fantastic presentation. I know that this is really going to inform the advanced manufacturing sessions that we hold in the fall, and we would welcome both of you gentlemen back. Again, we're very happy and very proud of this partnership that we've developed with CNS in these sessions. They hold record attendance every single time. We had over 245 participants at our peak today. So that is another great turnout. I want to thank everybody for the wonderful questions that you submitted. Again, we're very sorry that we can't get to all of them, but we do promise to have responses provided in writing. So keep an eye out for our next session coming up at the end of August, as Wilson said. Again, my name is Joseph Bastien, the Manager of Advanced Technologies and Processes with OCNI, with my co-host Wilson Lam, CNS G4SR2 International Conference Chair and Senior Nuclear Technology Advisor, Ontario Ministry of Energy, Northern Development and Mine in Ontario. And our guest speakers, Charles Carpenter, Senior Technology Officer, Nuclear AMRC, and Matt Smart, Project Technical Lead, in the Nuclear AMRC Machining Technologies Group. Gentlemen, thank you again for an awesome presentation today. We will make the video available later for you, and it will be distributed through the CNS as well. Thank you again, everybody. Stay safe, stay healthy. Take care.
Thank you.
Thank you.
Yeah, thank you.